Dear students, now I am going to explain Davisson and Germer experiment. So in this video, we are going to see the contents. First one is principle. What is the principle behind this experiment and how this experiment is constructed, and then working process, and what are the observations we are going to take, and how the wavelength can be calculated theoretically as well as experimentally, and then what is the final result of this experiment. Actually, this experiment is going to explain the wave nature of the particle. So before watching this video, first you watch de Broglie's hypothesis. So de Broglie has theoretically given that particle is also having wave nature. That is, matter is also having the wave nature. So he has given only the hypothesis, but experimentally it was proven by Davisson and Germer. So that part only we are going to discuss now. So the de Broglie hypothesis link has been given in the description box. Please watch it and then come to watch this Davisson and Germer experiment. So let us get into the video. The first point is principle. So what is the principle, how it is working? So now here let me give the introduction part for this Davisson and Germer experiment. Actually, they are following that Bragg's law. Okay, they followed the Bragg's law. That means they considered the Bragg's law as reference to prove that wave nature of the matter. Okay, so wave nature of the matter means here they considered wave nature of electrons, wave nature of electrons. That means the fast moving electrons are behaving like a wave. That is the principle. Okay, that is, fast moving is nothing but accelerated electrons. So the accelerated electrons are behaving like waves. Accelerated electrons are behaving like waves. So this is the basic principle for this experiment. Accelerated means fast moving electrons are behaving like waves. That means the electrons are having the wave nature. That is what they are going to prove. So to prove this, they considered one reference. That reference is Bragg's law. Okay, actually the Bragg's law explains, gives the condition for X-ray diffraction. Okay, so what is that X-ray diffraction? Simply let me explain. This is not important for this experiment. That means this is not related to this experiment, but this is the basic principle we have to understand. Actually, X-ray diffraction means here X-ray. X-ray is an electromagnetic wave. Electromagnetic wave. Okay, so this this is the crystal. Actually, this is the crystal they have considered. In the crystal, all the atoms, this red colors are the atoms. So all the atoms are arranged in a regular planes. Okay, this is the lattice planes, which is arranged regularly in the lattice planes. Okay, so if the X-ray is incident on that, it will be scattered. So the incident angle and theta and the scattered angle theta will be same. Okay, so this is the incident ray and this will be the scattered ray, and then this scattered ray will carry all the information about the crystal, So to get the scattering, they followed the Bragg's law. What is the Bragg's law? 2d sine theta is equal to n lambda. 2d sine theta is equal to n lambda. So they used this formula to get the X-ray diffraction. So this X-ray, the here main phenomenon is diffraction. That's what they used, X-ray diffraction. So by using this phenomenon, they got all the information about the crystal. Okay. So from this we can able to calculate lambda. Lambda is equal to 2d sine theta divided by n, right? So by actually in X-ray diffraction, they passed the X-ray, and they, by using the Bragg's law, they calculated the wavelength. Okay. So now Davisson and Germer also followed the same principle. Okay, instead of X-ray, they used fast moving electrons. Fast moving electrons. Actually, electron is a particle. It is a matter. Electron is a particle. Okay, if they get the same result, instead of X-ray, they used the fast moving electrons. If they get the same result, then they can say the fast moving electron is also having the wave nature. So this is what the basic principle of this experiment. Okay, so in theoretical calculation, we are going to follow the Bragg's law only. We are going to follow the Bragg's law. It gives the condition to get the diffraction. Okay, so they are going to follow, in our result, we are going to follow Bragg's law for the theoretical calculation of lambda by using this formula. And experimentally, we are going to use the fast moving electrons. If both the results are same, then we can say that the fast moving electron is behaving like a wave. Okay, so this is the principle. So this is the principle of this experiment. Accelerated electrons are behaving like waves. Okay, so now we are going to discuss construction and working of Davisson and Germer experiment. So this is the experimental setup for this experiment. Okay, let me explain one by one. So as we discussed already, so we need one crystal, then we have to pass the fast moving electrons, and whatever is scattered, that result we have to observe. So we need crystal and then electrons. We need crystal and electrons, and then we need the collector to collect the electron. So this is what the setup actually. The same thing only we have done like this. So what is that? So to produce the electron, we are using this electron gun. Okay, EG. So what is mean by EG? EG is nothing but electron gun. EG is nothing but electron gun which produces the electrons, which is connected to the LT. LT is nothing but low tension battery. What is LT? Low tension battery. Okay, and then this is electron gun which is connected to the low tension battery, and this electron is moving to this anode. This is the anode cylinder which is connected to the high tension battery. So HT represents the high tension battery, high tension battery. And then here we need the crystal. So electron is produced here. Okay, and then crystal here, which crystal we are considering? Nickel crystal. It is the target here. Okay, so the electrons will hit the nickel crystal only, and then the electron, this crystal is connected with one handle to rotate the crystal. That later I will explain during the working part. And then here one EC. What is EC? EC is the electron collector. What is the name for EC? Electron collector. That means this electron, this collector will collect the scattered electrons. Okay, and G is the galvanometer. G is the galvanometer, and this electron collector is fixed over the circular scale. This is the circular scale. This electron collector is fixed over the circular scale. So this is the arrangement. The whole setup is kept in the evacuated chamber. The whole apparatus is kept in the evacuated chamber. Okay. So let us discuss how it is working. So now you have the idea about the construction, how it is constructed. Let us coming to the working principles, how it is working. So first, an electron gun is connected to the low tension battery. So this electron gun will produce the electrons. So this is the electrons. Okay. So now what is happening means, here we kept one anode cylinder which is connected to the high tension battery. So the anode cylinder, anode means it is the positive charge. So it will have the tendency to attract the electrons. So this why this anode is used? Anode cylinder is used in the sense this anode will direct this electron. So this anode will accelerate as well as focus the electrons towards the nickel crystal. So the main function of the anode is it will direct the electrons towards the nickel crystal by accelerating as well as focusing, so that it is connected to the high tension battery. So how much voltage will be applied? The range of the voltage applied will be 30 to 600 volts. 30 to 600 volts. This is one variable we are using in this experiment. Okay, so the voltage applied in the range of 30 to 600 volts for the anode cylinder to accelerate the electrons. Now the electrons are fully accelerated. It is fast moving now. So which is hitting that target here, nickel crystal. And then here the nickel crystal is connected with one handle, so that we can able to rotate the crystal which is parallel to the axis of this incident beam of electrons. Okay, this is the handle given to that. And then once the electrons hitting the target, immediately it will be reflected. That means it will be scattered. So these are the scattered beams of electrons. Scattered beams of electrons, scattered beams of electrons. Okay, so this scattered beam is collected by the electron electron collector. Okay, this symbol I shown no. This is the electron collector which collects the electron. Okay, and then this electron collector is arranged over a circular scale. Okay, over a circular scale. Why? Because the scattered electrons will be in different direction. So to collect the all direction scattered beams, the electron collector is fixed over the circular scale. So the electron collector will move along the circular scale and it will collect all the scattered beam from different directions. So it can able to move from 20° to 90°. Okay, so this is the next variable. Okay, this is the next variable, second variable. And then this electron collector is connected to the galvanometer. Actually galvanometer means which shows the current. That means here the electron collector is collecting the electrons, fast moving electrons. Listen, fast moving electrons is nothing but current. Fast moving electrons are nothing but current. So this current will be recorded by the galvanometer here. So this current is nothing but intensity of the scattered beam. Intensity of scattered beam of electrons. Scattered beam of electrons, right? So this is the another variable. And then here one more angle I am going to represent. That angle is nothing but phi. What is this phi? Phi, this is the incident beam of electrons and these are the scattered beam. So phi is angle between incident and scattered beam. Incident and scattered beam. Scattered beam, right? And a special name has given to this phi, that is nothing but co-latitude. Co-latitude. Okay, so now listen, this is the working principle. So the energy gun will produce the electrons which is connected to the low tension battery, and this electron are accelerated and focused by the anode which is connected to the high tension battery, and this fast moving electrons hit the nickel crystal. The nickel crystal could be rotated by using the handle. So the axis of the crystal can be changed according to the axis of the incident beam, and once the electron hitting this nickel crystal, it will be scattered in all the direction. So that the scattered beam can be collected by the electron collector which is moving over the circular scale so as to receive all the scattered beam of electrons between the angles 20 to 90°. And this electron collector is connected to the galvanometer. This galvanometer shows the current which is nothing but intensity of the scattered beam. Okay, and another variable what I mentioned, that is phi, angle between the incident and scattered beam. So the experiment is keep on repeating for different voltage, different accelerating potential, and they keep on measuring this current that is current which is equivalent to the intensity of the scattered beam, and for each position of this nickel crystal, right? And they observed two things. One is V is equal to 54 volts. Okay, the voltage is equal to 54 volts and the angle phi is equal to 50°. So during this voltage, okay, they are getting the sharp curve in the graph. Okay, so keep on they are changing the range, changing this accelerating potential and measuring this phi value and the current value. So at one particular point, that is voltage is equal to 54 volts and phi is equal to 50°, they observed the sharp curve in the graph. So this is the evidence, this is the main evidence to prove the fast moving electrons are behaving as a wave. So now we completed the construction and the working part of the Davisson and Germer experiment. So let us see the graph, what they observed. So they drawn the graph like this. So in x-axis they considered the accelerated voltage and then intensity. That means what current they measured in the galvanometer. So when we draw the graph exactly at V is equal to 54, now you see root of 54 is equal to almost around 7.3. So around 7.3 they are getting the sharp curve in this graph. At the time the angle between the incident and the scattered beam is 5 is equal to 50°. So these two are the very important observations to prove the fast moving electrons are behaving like a waves. Okay, V is equal to 54 and phi is equal to 50°. So let us calculate the wavelength by using these two evidences. Okay, so now listen, this is experimentally we are going to calculate the wavelength. Okay, experimentally, and next we are going to discuss theoretically also. Theoretically also we are going to calculate the wavelength. So let us start the calculation. So experimentally That means they have observed two things. V is equal to 54 volts and phi is equal to 50 degree. Okay. We are going to calculate the lambda. So lambda is equal to h by mv. Actual formula for de Broglie wavelength is lambda is equal to h by mv. And then here the electrons are accelerated by the potential V. So that already we have discussed this formula in the de Broglie hypothesis. Please watch the video to get that information. So h divided by root of 2me into capital V. Okay, by substituting all the values of the constant, that is Planck's constant, and the mass of the electron and the charge of the electron, we will get the value lambda is equal to 12.26 angstroms divided by root V. Okay, so here V is nothing but 54 volts. So now V is equal to 54 volts we observed in this experiment. There we got the short curve. So lambda is equal to 12.26 angstroms divided by root of 54. So by substituting this value, we get lambda is equal to 1.66 angstroms. Okay, what is the wavelength value? 1.66 angstroms. So experimentally they have proven that lambda is equal to 1.66. So next we are going to discuss theoretical. So already in the introduction part I explained theoretically we are going to follow X-ray diffraction. X-ray diffraction. To get the X-ray diffraction, the condition is given by Bragg's law. Condition is given by Bragg's law. So the Bragg's law formula is equal to 2d sine theta is equal to n lambda. 2d sine theta is equal to n lambda. So how we are going to get this? Now listen, the nickel crystal, this is the nickel crystal. So in the nickel crystal, we have lot of crystal planes. So these are the crystal planes. Okay. These are the crystal planes. Okay, so here these are the lattice planes. Okay, and then in between these two planes the distance is there, no, that is called interplanar spacing. What is D? D is nothing but interplanar spacing. What is interplanar spacing? The space between the two planes. The spacing between the two planes is called interplanar spacing. This is the nickel crystal. For nickel crystal, the D value is 0.909 angstroms. So what is the D value for nickel crystal? 0.909. That is the distance between the two planes. Okay. And then D value already we know, and we have to calculate the theta. So how to calculate the theta value? Listen carefully. So this is the incident beam and this is the scattered beam. Okay, this is incident beam, this is the scattered beam. So it is incident beam of electrons and this is the scattered beam. Scattered beam. Okay, so the angle between incident and scattered beam is 5. So this angle will be 5. This angle will be 5, which is equal to 50 degree, right? And this angle, if you extend this, okay, so this angle is theta and this angle is the theta. The incident and the scattered beam angle will be theta. Okay, so the full angle of this will be 180 degree. So how can we calculate the theta? Listen, theta plus phi plus theta is equal to 180 degree, right? The first one, theta, phi and theta is equal to 180 degree. So here theta plus theta become 2 theta plus phi is equal to 180 degree. 2 theta is equal to 180 degree minus phi. So phi is nothing but 50 degree I said. So 180 minus 50 degree. So 2 theta is equal to 130 degree. From this theta is equal to 65 degree. So theta is equal to 65 degree, right? So now we know the D value and the theta value and N. What is N? N is nothing but order of diffraction. Order of diffraction. Here we are going to consider the order is 1. So n is equal to 1. So now we know D value, theta value, lambda value, so that we can able to calculate the lambda. So what is the Bragg's law formula? 2d sine theta is equal to n lambda. So from this, lambda is equal to 2d sine theta divided by n. Okay, so substitute all the values of that. Lambda is equal to 2 into d is 0.909, okay, into sine of 65 degree divided by 1. So by substituting all these things, we will get lambda is equal to 1.65 angstroms. 1.65 angstroms. Okay, so here experimentally they used fast moving electrons. Fast moving electrons. Okay, and here theoretically they used X-rays. X-rays are nothing but electromagnetic waves. Now you see, in both the place we are getting the almost same result, 1.66, 1.65. So what it proves for us, what it explains for us, the fast moving electrons also having the wave nature, so that is the result of this experiment. So we have calculated both the wavelength, and then we proved that the electrons are fast moving electrons are having behaving like a waves. So what is the result? The excellent agreement between the calculated wavelength theoretically as well as experimentally clearly showed that fast moving electrons behave like waves. Okay, so X-rays are electromagnetic waves, and the fast moving electrons also showing the same behavior. That is the reason we proved this one. So this is what the Davisson and Germer experiment. Okay, so please go through this. If you have any doubt regarding this experiment, you can ask me in the comment box. So thank you everyone.